In this part, we're going to analyze the code of this algorithm. First, we're going to build the array of blocks from the original array A. We're going to build the array B, which is the array of blocks, using this function. Build blocks. We take as parameters the original array A and the size of the original array and the size of each block BS. It will return the array of blocks. We're going to iterate over all the array A and build the array of blocks. And also we're going to build the list of elements of each block. Here, for each block, we're going to build the list of elements of each block. This type is a hash map or a map of each integer is associated to a vector. So each block, we're going to associate to that block the list of elements. Also, we're going to build the sparse table using this function. Normally, we know how to build the sparse table at this point. The time complexity of all these functions, of course, is linear time, as we have proved in the previous part. But the space complexity will be different from a function to another. For example, here, for the build the blocks, the space complexity is 2 times underscore b plus n, where underscore b is the size of the array of blocks. Why plus n here? Let's see. Let's come back to array of blocks. Here we have here the size of the array of blocks, which are and the underscore b. I call it here. This is the first one, and the second one is as you see here. The blocks list, or the list of element of each block, this map will contain as keys the blocks, so we have the same size here as the array of blocks, and for each block we have the number of elements of size BS, which is the size of each block here, computed using this formula. So we can say that the number of all elements here, it could be n, if we is more than n but we can say that is n. So we have here the space complexity is n plus the size of the array of blocks for the blocks list here, for this data structure, and also we have the size of our array of blocks one more time here for the array of blocks B. So we can say that time complexity is 2 times the size of the array of blocks plus n. The sparse table here, the space complexity of the sparse table is a number of rows times number of columns. Number of rows is the same size of the of the array of blocks here times the size or the number of columns using this formula. Also, we have to build two another maps. The first map, of course, later I will show you where we're going to use these data structures. These two maps, first, each block using this function, here, using the blocks list data structure that we have built using this function, this one. We're going to build a data structure that contains the blocks associated with their normalization binary string, and the norm block data structure, which is a map to which each normalization or each binary string will be associated to its first block. So we're going to have these two data structure. For this example, we're going to have these two data structure. As you see here, each block is associated to its normalization string, and also each normalization string, is associated to the first counter block. For example, here 1010, the first block is 0 that we have found 1010. 1100 is 1. You see. The space complexity of this, it will be, as you see here, we have the size of the array of blocks plus or times the size of each binary string. As you have seen, it's 2 times the size of the block. And also we have the number of blocks, in the worst case, of course, times the number of times the length of this binary string. So it will be 2 to a power 2 times bs. It's the number of the blocks, or the number of the types of the blocks, times the size of the number of blocks here, plus 2 power 2 bs, which is the number of types of the blocks. This one came from the size of the blocks, or the number of blocks, times the size of the normalization string. So we have this form. Plus we have also this formula. Using this formula, we find the number of bits, if you can say, we can say that, the number of total bits in that data structure, using plus the number of blocks here. from 0 to 15 for this example, plus 2 power 2 times bs, the block size, which is times the size of each, the number of blocks. So here, this will give me this one. In the worst case, we can for in the worst case, for each block, for each type, we can find the number of types equal to the number of blocks. So each type will have its own binary representation. So in the worst case, we have 2 times 2 power bs, the number of block of the types of the block times the number of blocks, plus the number of blocks. Oh, this one. Okay. This is for this function helps me to build these 2 data structure. You will take as parameters the blocks list, okay, as we have seen here, which is the list of elements of each block, this one, and we'll take also the size of each block, and will give me returns the blocks associated to each block associated to its normalization binary string, and each type of block or each normalization string will be associated to the first block that we encounter that normalization string. Then we have to build all the answers for each block, for each type of block here. Like for this example, we have just these 2 types of blocks. So in the worst case, of course, in the worst case, the time complexity is linear, as we have proved in the previous part. But the space complexity will be this: the number of blocks, how many blocks we have here, plus 2 times the number of blocks times the space of the 2D array of each block. Okay, as we have seen here, build for language normalization. I think I have done a copy paste, but I didn't change it here. Okay, this will be space complexity 2 power bs times, we have this is the number of types, times 2 times bs for each bit, for each character here, plus 2 times bs power 2 times 2 power 2 times bs times times the size of each 2D array of size I think log 2 log base 2 of sorry over 4 square. Okay, this is the space complexity. We can say this is our BS. Let's see quickly this function how it works. This function is easy for the build the blocks. We'll build the array of blocks using the same principle as we have seen in the previous parts. I don't know exactly which video. I think the video where we have seen the square root decomposition. And this for each block, of course, we have to put its element. The sparse table is easy. We have seen this in the section where we have used the sparse table. Come back for that. Now we're going to build the binary string or the normalization for each block. So we have to run over all the blocks and the blocks list. Okay. So for each block, we're going to build the Cartesian tree, or using the Cartesian tree principle, we're going to build the normalization string of size BS. The array is of size BS, which block here. So for each block, the first, so it would be the key here for this map. The key of this map, blocks list, which is the number of a block. We'll take the normalization string, the result of this function. This function is this one. As we have seen in the previous part, we have seen how to build this binary string. Of course, to be sure that we have used the first normalization string that we have encountered for this block, we can use a map that will mark each used normalization string. Once this normalization string is used, and never used again. Okay. How to build all ranges in normalization blocks? We run over this map, which will contain the normalization string as key and the block as value, as we see here. This is the key, this normalization string, this is the number of block. And for each block, we're going to build its matrix. So from the block list, we have to know which the elements of that blocks from the original array, and we can build its matrix or 2D array using this two nested loops here. It's easy to understand here. Once this matrix is built, we can affect or attribute to that normalization string that 2D matrix. Okay. This is the management array. This will use this pass table. We have seen this in the parts, and the part when we have used this pass table. Let's see the main program. This is the input. First, we're going to build the block size. We're going to compute, the blocks size, VS, as we have seen in the previous part. Then we compute the size of the array of blocks, and we build the array of blocks and the map blocks list using this function. Build this pass table. Associate blocks with their normalization. We have to use these two hash map here, or maps, C++. We compute all the answers. Okay, and for a query now, read the left and the right boundary. Of course, decrease one from each one, because in the problem, the left and the right boundary are one based indexing. If we have just one element on the train, just compute it. No need to do all that work. Same if the range makes a list of entire blocks. There are no parts of blocks on the left or on the right. Just use the pass table. Otherwise, which means the left boundary is not the beginning of the current block or the actual block, and also I forgot to mention here, the right boundary is not the end of the actual block. So what you have to do with that, you have to compute to which block corresponds the left boundary, and the right boundary, which is LB for the left boundary, RB for the right boundary. We have to compute it. And check if the left boundary is not the beginning of the current block or the actual block. Compute the beginning of the next block, because we have seen in the previous part. Same for the right boundary, if not the end of the current block, so compute its beginning. Get the normalization string of the left boundary, and also get all the answers of the left block. Of course, we're going to use the data structures that we have built in the pre-processing phase here. Same for the right block. And compute the minimum of the parts on the left and on the right, on the left part and on the right part, using the 2D arrays. You can come back to the previous part and see the example. I have showed this using an example, all this, of course. Then after computing the beginning and the end of the entire blocks, use this path table from that beginning to that end, and of course compute the minimum. But here, guys, I have an issue. Let's see it together. Frankly, until now, I did not figure out what's the problem. Let's test this code in these test cases. As you see here, all the test cases are passed except one, this one. I don't know why. If we see that on the CSES online judge that you see here, same code, they will have a wrong answer in this test case. So guys, sorry for that, but I have to debug that wrong answer to know that what's the source of the cause of that wrong answer, and also let's try to reduce the number of data structures. As you see, this is my first thinking of this solution. Maybe there are another solution that I'm pretty sure that another solution that use less data structures. Okay, I will try to figure out that. Please guys, help me to figure out the solution that use less number of data structures, and if you can figure out what's the cause of that wrong answer here. I will appreciate that, guys, if you tell me what's the cause. I promise you that as soon as possible, I will figure out that issue, and I will improve this code. If you don't understand the code here, guys, you can come back to the previous part and see the examples that I have shown, and try to follow this code. I will paste it in GitHub and try to follow each function how it works. This is the main idea. I'm pretty sure there are another better solution than this. Okay. For practice, try to answer this question. You can pause the video and try to answer it. So the answers here: can we apply the algorithm on static range sum queries? No. Static range minimum queries? Yes. Static range XR queries? No. Static range JCD queries? Yes. Static range maximum queries? Yes. Because as we have seen, we use this path table here. This path table works only on the idempotent function, which is if a function is idempotent, if f x give me x. Here, of course, the minimum of, for example, of 5 give me 5. The minimum of the function is min. Same for max 5 give me 5. The GCD of 5 give 5. Okay, but the XOR 5 is equal to 0. It's not 5. So the XOR cannot be applied here. Try to answer or to solve this problem from the sphere online chart. Let's see it together. It's a typical problem that used of typical problem of the range minimum query. You see here.